Thank you. So it is really a privilege to be here, and I really want to thank Rafi and the organizers for putting together this fantastic conference. And I want to add my challenge here, and this is molecular photochemistry. So this is about the interaction of molecules with light, and light is everywhere. So this is so omnipresent that probably we don't realize that this is governing many different processes in chemistry. So, okay, photosynthesis, emission, we heard about that. But light also governs circadian rhythms, takes place in the ozone generation. You can get beautiful pictures when you look at bioluminescence in animals. So, I mean, if you look, for example, to photosynthesis, this is a very simple and at the same time very complicated example how you can just get a very complicated or very simple chemical reaction in a very complicated way by means of light. So you convert light into energy, and you will hear much more in the next session and see how complex that is. If you look into vision, there you have one protein. This is retinal. Then you look a little bit closer to that, and you have here retinal in these cones and rods. You have this enzyme. And if you look closer, at the end, you're going to see that it's just one molecule, one chromophore. Yeah? This chromophore here, which is going to do the first step of this reaction. This is just in a very simple terms. This is a cartoon that just shows, okay, when the light irradiates, then you have a cis trans isomerization. So as I said, this is a cartoon because in reality this is much more complex. But this is really the first step of vision. A molecule does a motion, so this is from light to function, and this triggers a lot of different processes. So there is a number of important questions that it would be nice that we chemists can address, and I'm going to try to do this from the theoretical point of view. I mean, we would like to know what happens to the molecules when they are heated by light. And then a much more complex question is how can be light used to create new molecules, and how light can be just utilized to get new functions. And if we just get an answer to these three questions, then we can just make a big impact, because then we can just learn something sometimes from nature, and we can just mimic nature and convert this nature, fantastic nature machinery, into some technology, right? And one can even go farther and argue that if you understand very well how many of these processes are happening, and maybe you are not so happy with them and you want to improve them, one can even use some type of light, like shape light, to improve this type of processes. And I'm going to talk about the last topic, but these are questions that from my point of view is what molecular photochemistry is dealing with. So if you are able to solve these questions, you can make big impact in biology, in chemistry, in materials, or not just least because you can create some nice sun blockers in case you need it. But I mean, we are surrounded by many examples where really learning to design the perfect devices for light is nice. I mean, we need to, some people would be very much concerned how to protect their favorite drink from light, but we also need to protect our medicaments from light. We want to design different dyes for many, like maybe just for not having nice colors, but also for imaging. And nowadays, the field of materials is full of challenges because we want to learn how to get solar cells and very nice LEDs. So this is all about side-step chemistry. So apologize for now being quite simple. So we need to learn a little bit which are the main side-step processes that are taking place in a molecule. So let me put it just in a very simple way. So you have a molecule, and before the light comes, it's in the electronic ground state. Then it's excited, so typically it's going to populate some singlet states. And then it will just lose an energy in what is called non-radiative processes. So this just stands for internal conversion, which is just a transition between states of the same multiplicity. And it might also happen that you go from a state of one multiplicity to another one. This is intersystem crossing. And you can also have, of course, radiative processes in which you just return this photon to the ground state, fluorescence, and phosphorescence. And depending which ground state is this one, is the same one as we studied from, and somewhere else you might have a chemical reaction. So all the molecules that are outside there is all about understanding and looking which of all these processes is dominant on which of all these processes we want to optimize. Now, molecules are more complex than having levels. I mean, they have so-called potential energy surfaces. So this picture is now translated into this other picture, which shows that actually we don't have levels. We have a very complex topology that we need to learn in order to understand what the molecule is doing after irradiation. So, I mean, here is the same picture. You go to this second excited state. Now you want to go to the first excited state. You need to go through a crossing. We heard about that yesterday from Albert Stolov, like this conical intersection, because it looks like this way. This allows us to go to the lowest excited state, and then you also have other crosses or degeneracies with other states. You can go to other places. And from here, you can just return to the ground state or just go into some reaction. So if we want to understand and we want to learn about these processes from the theoretical point of view, we need to have a very clever marriage of two big fields. Right? One is the so-called quantum chemistry, and this is electronic structure theory. This is what is going to give us the roadmap. We need to learn in as much as our intuition is able to tell us which are the important surfaces, which are going to be involved in our excitation, which are the different pathways that my molecule could take place. But actually, if you want to see exactly what is happening, then you need to go into the realm of chemical dynamics. There, you can just watch the molecule evolving in real time, and then you can really see which of these very many pathways that are possible that you are hiking in the Alps, it will be really the molecule taking in real time. So this quantum chemistry and chemical dynamics, this means in the simplest, or let's say the most traditional way, is to solve two equations. So one equation, the time-independent Schrödinger equation for the electrons, and if you solve this equation, and there is many approximations to do that, you will get these energies, and you will get the topology of the surfaces, and you will even get these crossing points, and how strong are these crossing points, the so-called decouplings, which allows you to hypothesize one mechanism. If you are in the realm of the chemical dynamics, then you have to solve the time-dependent Schrödinger equation for the nuclei, and this gives you the actual pathway and the time scales and the quantum yields, if you're lucky. Now, what are the challenges? The challenges are to solve these two equations. These two equations, they are very difficult to solve. We've heard some things about that. We theoreticians, I think we go around the same thing all the time. It's very difficult, and the problem is for the quantum chemistry, I mean, I would just argue until an hour ago that the problem is the accuracy that you get for the side states. I mean, for the ground state, the methods are better prepared. We know how to do it better. For the side states, the accuracy is an issue unless you do full CI, which normally is not possible until Todd Martinez showed that now you can do it. So typically what you would say is that you have an accuracy of 0.2 electron volts. This might not seem much for some. I will just try to convince you that this can be really very bad in so many cases. Now, these energies here, they also enter the Hamiltonian that you really have to solve for the chemical dynamics. So if you have a problem with your electronic structure, this problem is going to be carried out to the dynamics. So this means that for dynamics, I mean, you are just plagued by the accuracy that you have for the electronic structure. And at the end of the day, what this means is that the time scales that typically you can solve, they are too short, right? If you're lucky and you use a good method, it's going to take some time, and then you cannot really propagate for a long time. And we have heard that many of the important processes, they are multi-scale, right? So this is going to be about this ultra-short, like in femtosecond time scale, looking how these molecules are moving. But for the important processes, you have femtosecond, picosecond, nanosecond. So this is very tough, how to go this way. Now, if you want to see how good is a method, normally what theoreticians do is just to take a data set, okay? So I just want to illustrate you, I mean, how these errors can demotivate you somehow. So this is just a database from Walter Thiel. So it's like 50 molecules, 50 chromophores, different sizes, different types, and then now you take different methods, so it does not matter what this is. There are different methods for electronic structure. So some of them are like expected to be more accurate. Others you don't know, especially in the frame of time-dependent DFT. You never know what you have Well, you see here the errors, the mean errors for these 50 molecules. So some of these methods are not so bad. You also see some errors are positive, some errors are negatives, or anything, right? In the best case, some of these methods, they're about 0.2. In other cases, they are larger. And it's even worse because the accuracy of the methods, I mean, this is a mean average, right? And then when you just have a new method or something, you always do that, and they show the mean error is this, and then you're happy with that, but the person or the student who is going to use the method doesn't want to have 50 molecules, wants to have 1. And if for this one, the method is very bad, then, well, you have a problem. And indeed, the accuracy of the method depends on the system. Even if you take a molecule, the accuracy depends on the electronic state that you are describing, and the accuracy depends on the system size. So it's not so good, and we're talking about quantum mechanics, right, which is like the best that we imagine that we can do with these methods. So I'm going to show you one example. I mean, this very simple small molecule, thioformaldehyde, okay? So there are 3 side states of interest. So here I have a lot of methods. This is the experiment. The molecule is radiated by light, and I just look how all these electronic states look like. So I would say, well, I mean, these are methods, does not matter what they mean. I mean, they are like quite accurate, less accurate, some of the DFT functionals. I mean, in general, this is a dream situation. The 3 states, they are ordered in the same way. The character doesn't change. I mean, you would say, well, probably I can live with that. I mean, most of the things are going to be qualitatively the same, so you could just live with many of these energetic descriptions. Now these are the side states. So the light comes, and then I just get populated. I see how these states are populated. Now let's do dynamics. Now when you do dynamics, it's not anymore important just only what happens when you assign the molecule, but also what happens on this topology that you are going to visit. So this molecule is phosphorescent, so we just ask ourselves, how fast is the intersystem crossing? Can we see intersystem crossing? So can we populate the triplet states within 1 picosecond? And then these methods predicted no, this method predicted yes, this method predicted no, and within the functionals you have also yes and no. Okay, we know these methods are very accurate, so they should give the correct answer. So there are 2 things here. One is, looking at these energies, you have no single chance to make a prediction whether you are going to populate triplet states or not, given on these accuracies, okay? The answer is, if you, I mean, this is a small molecule, so you can investigate the potential energy surfaces, and you realize that the accuracy that you get for this, let's so-called Frank Condon, it has nothing to do with the accuracy that you get later in the potential energy surfaces that actually the molecule is exploring, right? The second thing is, if you would not know the answer, I mean, that would be a very frustrating situation, right? Because you don't know what to believe, yeah? So stationary quantum chemistry can be quite satisfactory. I would say this is all in all quite satisfactory, but from the dynamics point of view is quite depressing, okay? Now, maybe this is the reason why still this quote from Albert Einstein is still valid. I mean, in theory, something nobody believes. Is that the person who makes it means, like, if you're a theoretician, you have to be very careful, and you have to benchmark, and you have to validate very careful which method are going to use. I mean, I believe that the life of experimentalists are much easier because everybody believes these are the correct numbers. We learn that sometimes this is not really true. So is this hopeless? Well, I think it's not hopeless. It's just sometimes a painful way. And in the rest of my time, I want to show you some examples of our own research, how we have been like kind of navigating through all these complications just to get some answers or some insight into some interesting problems. And the one I picked up is just the interaction of DNA with sunlight, because I think this is quite intriguing. So, I mean, you have DNA, and this is composed of very simple organic molecules. So DNA is a very important molecule because it contains all the genetic information, and if you alter DNA, you get cell disorders, you get cancer. So you would expect, I mean, that being DNA composed of organic molecules, they are not really the best, most stable systems under exposure of light, and we're constantly exposed to light. And it's very interesting that these molecules here, these nucleobases, are photostable. What does this mean? So photostable means, I mean, we're constantly exposed to light, so these molecules are excited, but they find a way to return to the ground state very efficiently. So in summary, I mean, one could say, I mean, they just convert light into heat in a very efficient way, and that's why it's photostable, and this is why it's good for us. And the mechanism that has been proposed for that is actually a non-radiative mechanism. So it's just depicted in this beautiful picture that was just proposed by Donkey. And there have been other people just proposing this type of things, like Donkey, Blancaform, Merchan, Marianne, from the statical point of view, and also Lischka and Todd Martinez, also from the dynamical point of view. So the molecule gets excited, it goes into some electronic excited state, and then you find these conical intersections that allow you to return to the ground state ultra fast. By ultra fast, I mean in a femtosecond, sub-picosecond time scale. So we, as I said, there have been many people looking into that and just proposing different flavors of these mechanisms in different nucleobases, sometimes depending on which method you use for doing the calculations. And we wanted to contribute to that. And in 2011, we just developed a method that is able to consider simultaneously the singlets and the triplets. So until now, I mean, or until that time, most of the dynamical techniques for exploring the full dimensional space with trajectories, they were only considering singlet states, so they were just concerned with internal conversion. And we had a development that allowed us to look into triplet states. So this was deemed by many people as redundant because, I mean, especially you have organic molecules, but they don't have any heavy atom, you don't have a substantial spin-off coupling. In the system crossing, I mean, there is a long tradition of chemistry with the triplet states, but they all are populated in the nanosecond time scale. So this is going to take very long. So nobody was thinking that the triplet states would just play any role in the ultra-fast time regime. So we did dynamics on the system, and then this is a typical picture you get when you do this trajectory side-state dynamics. So you get the evolution in time. This is logarithmic scale for the side states which are involved, and you see here very beautifully, I mean, the S2 is decaying, the S1 is decaying, the recovery of the ground state is very fast, it's ultra fast. I mean, you see here within a few femtoseconds, the ground state is recovering, so this is the essence of photostability, right? But then we saw something quite strange, and it was like the triplet state was also populated in this sub-picosecond time scale. This was not expected. That it would play a role in the ultra-fast time scale. And we also looked at other pyrimidine nucleobases, and we found that in all of them, for this type of, let's say, simulating experiment of these nucleobases, this was also the case. You had these triplet states. The beauty of this type of calculations that we theoreticians do is that you can get a mechanism, so you can translate these trajectories into potential energy surfaces. You don't have to explore these potential energy surfaces in advance all over 3n minus 6, but the trajectories, they tell you what you have, and you see from this picture it's not as simple as going up and going down. You have many ways to go down, so you go into the surface, and you have a way to return to the ground state, another way to return to the ground state, a way to go into the triplet, and you can make a sort of a movie of which are the key structures that they're being visited by the molecule through this excitation adventure, right? So it starts in planar, and then some of these groups are just moving around. So we have this tool, and now we thought we can start doing some chemistry. So here I have some game for you. So this was cytosine. This was in the keto form. Okay, so you have here an aldehyde, and then chemists like this. Let's change the group, and then let's try to guess, or let's try to predict what is going to be the result of that. Now I put the enol form. Now I have here an aldehyde. So when you do dynamics, then you see dynamics is very different. I mean, these molecules are not so different, one would think, but they are. I mean, here the intersystem crossing is suppressed, dynamics is much slower. And in order to understand that, you really have to go back to look into these potential energy surfaces, to look into these structures, just to see what is happening. Like in this case, blocking of this carbonyl group. This carbonyl group was one of the main ingredients to go into the triplet, and once you block it, then you don't have that. You can also play with substitution. So now we do something which, so we substitute this oxygen by a sulfur. So this is a very small change from the chemical point of view. You would expect these two molecules are very similar. And chemically they are, but photochemically they are not. So when you do the simulations here, you realize that something very different happens. I mean, basically the photostability, the returning to the ground state is kind of blocked, and instead you have a lot of intersystem crossing. So this has also been backed up by experiments. Actually, the simulations are not perfect because we have like 60%. The experiments they show like something like 100%. And this is something that occurs in all these TO bases. So whenever you take a nucleobase and you substitute by sulfur, you get a different mechanism, and that you can understand looking into this in these trajectories that you are excited, to this pi star states. You can go down to the lowest level, but now this funnel, this conical intersection to the ground state is not anymore accessible because this has been kind of stabilized by the presence of the sulfur, and then you trap here in this minimum. So you cannot go down to the ground state. Instead, you find the triplets, and this is what makes that now you have triplets. Triplets are bad because you have radicals, right? So that's why we don't want to have these side-state reactions happening in DNA. And here you see that just the introduction of one single atom has switched the photostability into phototoxicity. So these TO bases, they are so similar to the nucleobases that they were also used as drugs. As immunosuppressant drugs, and then they started realizing that the patients treated with that, they had more propensity to have skin cancer, and this is the reason, right? So this favor of photostability is gone, but you have this creation of these triplet radicals, and this is bad, and then this is what ultimately will just generate a cancer. Now, you can always turn things up, right? So if something is bad, you can just convert it into therapy. So now that one understands really how this is this working, I mean, there are just ideas and concepts to use this in therapy and just create damage where you want to have this damage, right? Because this is a perfect Trojan horse that you can introduce. Your DNA will just take it because it's like a nucleobase, but will have very different photochemical behavior. So I talk about photostability and how the DNA has a sort of a defensive mechanism against a sun blocker, a perfect sun blocker for the sun, or maybe not so perfect because maybe there is also some transition to the triplet states. But indeed, I mean, in DNA you can also have damage. So there are many ways in which the DNA can be damaged by sun. So you can really have some chemical reactions going on there. Here, summarized into this picture. And one of the most abundant lesions in DNA is just the dimerization of thymine. So this is an infidelity. So the thymine will not pair with the adenine as it should, but just will just kind of pair with another thymine stack there. So this reaction, can happen just by direct irradiation, can also be photosensitized, because even if it's the most abundant photo lesion, it's only 3%, which is good for us. I mean, there is a very efficient repair mechanism in the body just to deal with that. And it was studied also from the experimental point of view, and was seen that it was ultra fast. So within 1 picosecond, this dimer was formed, and there was some debate about whether this reaction happens through singlet states or through triplet states. And then we just thought it would be a nice opportunity to put our code there to work. So just to make the story short, I just show you one of these trajectories. I mean, through this manifold of states, you also have the chance to see that that's complicated, right? You have many states which are involved. You also see how the molecules are dancing, and they're just kind of flirting to each other, and eventually they are forming one bond and almost concerted within few picoseconds. In the spirit of the Goodman-Hoffman rules, they are just forming this dimer. And if you pay attention to the colors, the singlets are blue, the triplets are red. Many triplets are close to the singlets, but you never go to the triplets. So none of the trajectories show that. So we just concluded that there was no triplets involved in the direct formation of this thymine dimer. Okay, so in the last 5 minutes, I will just going to go back and just think about something else. So we're talking about what happens when DNA is irradiated by light. I mean, I was just showing very simple, nevertheless time-consuming computational experiments for us, but just referring to, let's say, some also simple in the sense conceptually simple experiments, trying to understand from the bottom of the conceptual line how is this photostability in these organic molecules happening. And something which is kind of interesting is to think, well, DNA is excited by light. What really happens when DNA is excited? So how delocalized is this photoexcitation in DNA? So it's just one nucleobase which is excited, like these simple experiments are just trying to model, or is it dimers, and you have stacked dimers or Haring bonding pairs? Is this more oligomers? So this is a question that looks very naive, but has been dealt with in the last 50 years, and there's a lot of studies dealing with that. So I just want to focus here in polyadenine. So the people have been wondering how many nucleobases are involved in these collective excitations in the single-strand polyadenine. Okay, and the predictions are everything. You have predictions saying that it's a very localized excitation. You have predictions which are very delocalized over 7, 8 nucleobases. I mean, everything in between. In this picture, you see the spectrum of the monomer, of the adenosine monophosphate, and the spectrum of the polymer. Yeah, and based on this very strong hypochromism, the people argue, well, this is very much, so the intensity has been much lower, so this is a clear indication that this excitation should be very much delocalized. Then some people say, well, yeah, but look, I mean, these two spectra, they just peak almost in the same place. So, I mean, if this polymer spectral peaks in the same place where the monomer is, this is a clear indication that this is very much localized in one monomer. So there have been studies for all flavors, and we decided just to look into this problem with brute force. So nowadays one can really do, nevertheless, really very big calculations. So we took a very long strand of 20 adenines. Okay, you start just sampling, so you have to get the right conformation. So we sample for 50 nanoseconds, then you take snapshots. And then we use these multi-scale methods that were very nicely introduced by Warshall the first day. So you separate part of the system that you're going to use with quantum mechanical methods and part with molecular mechanics. So in the QM part, we take 8 nucleobases. Okay, we took a lot. So this was like the limit that the people were arguing that you would have something there for localization. 8 nucleobases in the QM part region. And we had 100 snapshots. So this means, well, we're calculating because we have many nucleobases, you have to calculate a lot of states. So we have 6,000 states, which actually, it was brute force. It's not complicated, but you have a lot of data, and then you have to figure out how to deal with the analysis of the wave function in an automatized way. And when you do all that, that's what you get. This is the spectrum, okay, that you saw before, experimental. That's the theoretical one that agrees quite well. And this is the decomposition in terms of the delocalization length. So how spread is this excitation? And you see that actually almost, here. Almost 50% is the localization over 2 nucleobases. You have another 25% or 20% of the localization in the monomer, and another 20% in the 3, in the trimer, and then, I mean, about 6 is 0. So these tell us that actually the average localization is something like about 2 nucleobases, and with this I think that we can just put end to this controversy. And now you're going to start thinking what this all means in terms of DNA and excitation. So it's nice to see, and it was not ever demonstrated before, that this delocalization spreads through different nucleobases, because this is like what would you do with your money? You want to win, you will just buy different type of actions. So for the DNA, it's something like the same. It just spreads between 1, 2, and 3. And you are in 1, this is good, because this is the key for photostability. So the thing is, like, maybe nature could not do better, and then the price to pay is like he also had a lot of the 50% in the dimers, and you see that the dimers, they are just the origin of this photo damage. So then he had to invent some repairing. And what is the function of the 3 nucleobases? I don't know. So we have not done calculations with 3 nucleobases. So with this, I'm coming just to the end. I just wanted to illustrate you, I mean, how despite all the difficulties, you can get some insight. And I think that only by understanding in a let's say traditional way, how the UV radiation relates to the molecular mechanisms, we can get some predictions and we can just design some interesting molecules. And I am convinced that theory plays a big role here. Okay, I mean, of course, machine learning maybe will just prove me to be wrong, but theory plays a big role, and hand in hand with experiment. Although sometimes it feels like you are in a small boat in the big ocean, right? You don't know really how you are going to reach your goal, but you have to be positive. You have a boat, you don't have to swim, so eventually you will just get to your goal. So I just want to thank my group and all of you for your kind attention.
One interesting feature that comes to mind here is that you found in a number of cases, I think mostly multichromophoric molecules, quite fast singlet to triplet transitions. I think I noticed something like one, because I wonder if you could comment on the physical and chemical origin, like is it that the spin orbit coupling and the crossing is especially large, or is it more that a lot of trajectories are going the crossing region?
Okay, thank you, Benny, for this nice question. So indeed, I mean, I didn't want to show, we did a lot of calculations of looking how is intersystem crossing in some systems. I mean, our code is also public, so also people are doing that. And in all the cases, I mean, for these like organic molecules, like cytosine, you have a small spin orbit coupling. So in average, it's something like 20 wave numbers, right? In a maximum maybe like 40. So you think in ruthenium 3-sp deal, I mean, we will be like 400, like 1,000. So it's very small, but the trick is that you have almost degeneracy. I mean, the cores for the singlet and the triplet, they come together. So they have the chance to interact, and if the coupling is, let's say, larger than the gap that these cores have, not in the static picture that you imagine when you calculate the side state, but in the dynamical picture when you see these molecules evolving, then you're going to have a non-zero probability to have intersystem crossing.